Welcome, folks. We are meeting today for the first tutorial session, and in continuation, the lecture number is 39. We'll be solving some examples from every chapter, and you'll have to make some kind of a self-discipline very much, that I'll give you the problem. You go and get the paper and the pen and arrangement that you can attempt to solve the example. I may not make a break, but you can stop after the first example. After every example, you can stop your the display here of what I'm giving you and attempt, and then proceed to see the solution. This is a requirement and a self-discipline requirement. You should do that. You are at freedom to skip that, but don't skip that. Make a break after noting down the example or having the example on the screen and attempt. I'll give you a few minutes. I may not give you a few minutes. You can take a few minutes to proceed. You should do that. Otherwise, you may not be able to learn it properly. So this is the first tutorial session, as we put it to be. Yeah, a few real-world examples and numericals. I have tried to apprise you with the numerical examples which are real world. I mean to say, which give you the conditions followed in practice. For example, if it is a cable, the size of the cable is from the actual size of the cable, etc. So if it is about lightning current, from the actual value of current injected on the transmission line, like that. The values what you will come across are the real world or actual values in practice in day-to-day life. So let's begin with chapter number 1, and there are something like 15 examples from the 10 chapters, and let's begin with the first example. Yeah, you have to calculate the line current in kiloamperes for a 3-phase star connected 650 megawatt synchronous generator that generates power at a voltage of 21.5 kV at a power factor of 0.9. It's a very simple example. So after this, I'll just apprise you, give you some hints how to solve it, and then you make a break, your own break. See, we are asking you to calculate the line current for 650 megawatt. That means power factor has to be taken into account. Volt, amperes multiplied by the power factor, which is given 0.9, that equals to be 650. And the generation voltage given here is 21.5 kV, and you whenever in power system we refer to a voltage, rated voltage, you can say, the rated voltage is always given line to line and RMS value. So 21 0.5 kV is line-to-line voltage, RMS, in RMS. In power systems, in AC power frequency, unless and until it is mentioned peak value, you should always take it for granted that it is RMS value. And the rated voltage is always given to be line to line. For example, 11 kV, 33 kV, 400 kV. These are all rated voltages line to line. And you are being asked to determine or calculate the line current, the current in every phase. So you should now make a break and try to solve. I may not wait, but you have to wait to proceed to see the PPT. Okay? Welcome back. I hope you made a break and calculated. When you have calculated, then you should proceed. As you know, a three-phase system, the power in a three-phase system is given by root 3 V line I line cos phi in watts. As this is a very well-known formula given in any three-phase system. This you must have learned in the basic courses on power system. And when you put the values, V line is given to 21.5 kV into 10 to the power 3 volts. Cos phi is 0.9, and the power, three-phase power, is given to be 650 megawatt. That is 650 multiplied by 10 to the power of 6 watt. You convert everything in watt, volts, and you will get the current in amperes. So you can determine the current in kiloamperes, as you can see it here. 650 multiplied by 10 to the power of 6 divided by root 3. When voltage is given in volts, but this would work out to be, you have to divide it by root 3. Sorry, 10 to the power of 3. Once again, you have to divide it, and then you will work it out. It should have been in kiloamperes it has been given. So for getting it in kiloamperes, not in amperes, because it is volts and watt. So this must be divided by 10 to the power of 3 to make it kiloamperes, isn't it? So that will work out to be 19.39 kiloamperes. This is the line current in every phase of 650 megawatt generator. By the way, we are manufacturing in our country 650 watt thermal power generators, and these are normally two-pole generators and manufactured at BHEL Haridwar. I've gone and seen how the construction is. Can you imagine a line current of the order of 19.39 kiloamperes? How much a fan in your house consumes power? Current. What is the current there? 230 volts divided by 60 watt. It is there, divided by 230 volts, and the current. Current would work out to be in fraction of an ampere. Fraction of an ampere. Whereas the current in the generator phase current in the generator winding is of the order of 19.39. When such a large current flows in the winding, what what will happen? The biggest problem would arise with I square R losses. And I is so high, 19.39 kiloamperes. And so you try to bring down the resistance of the windings as low as possible, and still very high amount of heat will be produced. So the temperature of the winding cannot be raised beyond a certain limit because the insulation provided to the winding is limiting the maximum temperature of the winding material. So depending upon the maximum temperature withstood by the insulation provided to the winding, you have to restrict the temperature rise in the on the conductor, which is in contact. The insulation is in contact with the conductor, winding conductors. So what will you have to do? You may have to do, or you have to do, a very strong cooling system in such generator. Let me tell you, in such winding, there is, I'll draw it here, this here, and this is the conductor. So I have made, and this is the insulation provided to the conductor. So this is hollow. This is a passage provided for the flow of water as coolant. The water flows through, this is the copper conductor, and this is your dielectric insulation. So the to limit the temperature rise of the conductor, copper conductor, which determined by the maximum temperature withstood by the dielectric, you flow the cooling water, circulate the cooling water, you take away the heat. In a closed cycle, it is circulated. You take away the heat, which goes to the atmosphere, and then the cycle of cooling water completes. This keeps on going. Imagine here, as we have mentioned, water is the biggest enemy of any electrical insulation. But here you have to use water in closed cycle, circulate the water in closed cycle. So a lot of construction precautions and construction care has to be taken to make such conductors, and that too, I mean, the whole conductors in the generator, this has to be followed. The size of the generator, that is why, increases like anything when you go for generating such large amount of power to the tune of 650 megawatt. If you have an opportunity, you must visit Haridwar and see them. Now, a very important question I would like to discuss here. You would say, why don't we increase the voltage? This is 21.5 kV. If we increase the voltage, the amount of current would be much lower, isn't it? Then what happens is that, just a minute. I was just wondering whether I have said this correctly or not. You know, this will give you directly in kiloamperes, isn't it? No, you have to, yeah, to cancel this. And this cancels 26, and 650 divided by 21.5 multiplied by root 3 into 9. That will work out to be 19.39. Yeah. Hmm? Okay. Yeah, it's correct. Yeah. Well, back to the question. If you could increase the voltage at which the power is generated above 21.5, the the magnitude of the current would come down. Then why don't you do that? Why don't, in practice, people do that? There are limitations. The winding insulation is provided with insulating tape, kind of an insulating fiber, for example, fiberglass reinforced plastic tapes. There are a number of kind of tapes available, which people use for the generators. And the taped insulation, there is a limit for to withstand the voltage, because when you provide insulation by tape, layers of tape above each other, there will always be air pockets in between. And what would happen in those air pockets? Can you imagine? Air pockets are the weak points in the solid dielectric. And what happens there? Partial breakdown phenomenon takes place there. So if you increase the voltage, the intensity of partial breakdown in the air pockets formed in the taped insulation would increase, and it may not provide you the life you desire. So, especially in case of generators, there is a limitation of maximum voltage at which the power is generated. Unlike in the case of transformers, where the whole insulation problem is taken care by dipping the winding and core and everything in insulating oils, so it can withstand much more much more voltage and electric field intensity. So, unlike in transformers, in generators, you cannot do that. It is not dipped in oil, and then this kind of an arrangement has to be done, and you cannot produce the power at higher voltages. The maximum voltage at which the power is generated in the world is 33 kV. So this example, and also taken care to have learned. Now I'll give you the next example. Yeah. The next example is about power cable. That is a single core 500 kV coaxial lead covered power cable insulated with XLP, cross-linked polyethylene. Insulation has the following construction details. Let me tell you one thing. The coaxial cable, that is the inner conductor, that is the main conductor of the cable, is at high voltage, and the outermost conductor, which is provided in this case with the help of a lead sheath, we call it lead covered or lead sheath covered. You could also say lead sheath, we call it. Lead is a very heavy metal, and to provide lead sheath as a cover to the main cable construction, that is the conductor and the insulation is no joke. Lead press are required, and the lead melts at not very high temperature. So that temperature is brought when the lead can be extruded. It is extruded in one shot over the insulation, and you have to take care that the temperature does not damage the electrical insulation, because very hot lead sheath is extruded on the top of the insulation, cross-linked polyethylene insulation, and no damage should take place because it is immediately cooled under water conditions. Water should not go inside the lead, but it is cooled from outside. Because if water goes in cross-linked polyethylene, the cable will be damaged. Water is the enemy of insulation, which in no way water should penetrate inside the insulation. So it is cooled from the top of the lead sheath to bring down the temperature as early as possible before it makes any damage to the insulation. So the dimensions are given here. The copper conductor diameter is 30 millimeter. Extruded semiconductive layers on the conductor. We have discussed that to achieve a smooth surface over the stranded wire conductor, the main conductor is made of number of thin wires, because if you take a solid conductor, the flexibility will be not there. And to make the conductor to be flexible, because you need to roll on the drum for carrying it away, then unroll while laying. So you need flexibility in the cable. And to achieve the flexibility in the cable, you make the main conductor out of stranded wire conductor. So the stranded wire conductor may not have a smooth a smooth finish over it. To achieve the smooth finish of the conductor, copper conductor, in such case mainly copper, sometimes also aluminum is used for the main conductor. So a semiconductive layer on the conductor as well as cross-linked polyethylene insulation are both of 2 millimeter thickness. So 2 millimeter thick semiconductive layers are provided over the main conductor as well as after providing the insulation over the insulation also. And can you imagine in such a case, I'll give you just one hint. A semiconductive layer over anything becomes part of the material over which it is provided. So when it is provided over the conductor, the semiconductive layer becomes part of the main conductor, which acquires the voltage. That means the semiconductive layer also acquires the full voltage, that of the conductor. When it is provided over the dielectric or the insulation, and over the dielectric or the insulation, you have provided a lead sheath. Lead is a conductor once again. So that means the semiconductive layer over the insulation becomes part of the lead sheath. That means the dimension of the outer conductor. You can say that provides you the dimension of the outer coaxial cylindrical arrangement. So the semiconductive layer, mind it, acquires the potential of the conductor in contact. Inside the conductor, it is the main copper conductor carrying the high voltage, and over the insulation when lead sheath is provided, which is at ground potential. Mind you, the lead sheath is always at ground potential. It is grounded also in the circuit. So the semiconductive layer below lead sheath, you can say, determines the dimension of the lead sheath. Now, extruded XLP insulation thickness is that of 34 millimeter, having 34 millimeter. The thickness of the lead sheath over the outer semiconductive layer is 4 millimeter. So you have to do one thing. You have to draw first the sketch. There is concentric circles, nothing else. No? Concentric circles you have to draw the conductor, then over the conductor the semiconductive layer, then over the semiconductive layer the cross-linked polyethylene of 34 millimeter, then over the 34 millimeter again 2 millimeter semiconductive layer, and over the second semiconductive layer of 2 millimeter thickness, you provide a 4 millimeter thickness of lead sheath. So you draw the circles and define the dimensions. Okay, if you draw the circle properly, you will learn properly the inner and outer radiuses for the coaxial cylindrical arrangement. Then calculate the maximum and minimum electric field intensities in the cable. You have learned it in this chapter. Then calculate the Schweiger factor. You remember the Schweiger factor is E mean by E max. So in the B, you have to calculate the maximum and minimum field intensities. So you calculate with the maximum field intensity and the mean field intensity, the Schweiger factor. Mean field intensity would be given by the voltage divided by the thickness between the two electrodes. You have to carefully determine the dimensions to get the correct answers. And then, when you get the value of Schweiger factor, eta, that is your eta you can say is E mean by E max. So E max you will determine in B, and E mean is U by D, the thickness of the dielectric, that is given here to be 34 millimeter. And when you are working and you are working in RMS value, so everything will be in RMS value. And but you have to carefully determine U. What is the U here is the potential across the dielectric, potential difference across the dielectric. That means between the phase and the ground, and that will be not 500 kV. Instead, it will be 500 divided by √3. That is the concept of U naught. I have given you the that is the potential difference across the dielectric you have to find out, and that is not U, the rated voltage. The rated voltage, as I mentioned, is always given between line to line, but here the potential difference between the conductor and the outer conductor of the coaxial system is line to ground, and that is U divided by √3. U rated, you can say that is equal to U rated, or U N also. Sometimes people give it divided by √3. Okay, and these, what will be the capacitance per kilometer length? We have made derivation for the capacitance. You should consult. You can, in the meantime, consult your notes or the book where I have given it from. It's all given there. And then estimate the charging current per kilometer length of the cable at rated voltage. So the charging current omega Cu will be omega Cu. Omega is the frequency in radian, that is 2 pi f, and the capacitance you have already calculated and applied to the voltage across, multiplied by the voltage across. Why? The charging current per kilometer length of the cable will be nothing but the charging current of the capacitor formed by the cable, or the dielectric of the cable. The capacitance, the dielectric always forms the parameter capacitor or capacitance. So the capacitor formed, what will be the charging current in the capacitor? Omega Cu, that is the current that you will have to calculate. Okay, so you should make a break now, and in the meantime, I will not wait. I'll give you the solution then immediately. Okay, but you should make a break, try to solve, and then proceed. Fine. Yeah, here's the diagram. As you see, the first answer to the first question is the diagram. This is the copper conductor, 30, you see in the middle, copper conductor, the 30 millimeter in diameter. And over the conductor, a 2 millimeter thickness semiconductive layer is given. The two semiconductive layers are shown here in dark circles, and then comes the 34 millimeter thickness of the XLPE, and then on the topmost layer is the lead sheath of 4 millimeter thick. You must know. So what will be your RO, what we call it to be RO, the what will be the RI, the inner radius of the coaxial conductor system. That will be 30. The radius, inner radius, will be 15 millimeter plus 2 millimeter. So RI works out to be equal to 15 plus 2, that is 17 millimeter. Okay, then RO, RI and RO are actually the inner and outer radiuses of the dielectric, where you calculate the minimum and maximum electric field intensity. So RO will be nothing but simply 17 plus half of plus 34, sorry, plus 34 millimeter thickness is the dielectric. Yeah, insulation thickness is 34 plus 34. So that gives you how much? 51, isn't it? Is equal to 51 millimeter. If you have determined RO and RI to correctly, then not much is left. And U naught, you can imagine, U naught will be equal to 500 divided by root 3 kV. So these are the three things you must calculate properly. Yeah, here are the calculations. So U naught 500 divided by root 3 gives you 288.68, and RO and RI, as I have explained, works out to be 17 and 51 millimeter. So hence D, what we call it to be the thickness of insulation, is RO minus RI, or it is also given as 34 millimeter. So Emax, you know, is U naught upon Ri, that is at the maximum field intensity is at the inner radius of the insulation, that is Ri, ln Ro by Ri. So when you put the values 500 divided by root 3, 1 by 17 Ri, that is, and 1 upon ln 51 by 17, that works out to be 15.456 kV per millimeter, Emax. And similarly, you work out the E minimum, putting sorry, it is misprint here. This should be RO, not RI. RO, corrected. So that will work out to be 5.152 kV per millimeter. That means the thickness of insulation the minimum field intensity will be in the at the outermost dimension of the insulation thickness, or RO. So something very interesting you work out. If I correctly remember, something like 50 years back, this maximum field intensity was limited to only about 4 or 5 kV per millimeter. Over the years, in half a century, the technology has developed so well that one can increase the maximum field intensity to the tune of 15.4. That means 3 times higher maximum field intensity can the material, and the material, I mean to say insulating material, and the insulating material finish can today withstand 3 times more maximum field intensity as compared to 50 years back. So this is the result of the development. But why do you want it? Why do you want higher field intensity to be withstood by the dielectric? When you increase the maximum field intensity, the total thickness of insulation layer provided would reduce considerably. So the total dimension of the cable reduce. So the material invested there reduce. So that brings down the cost. And if you can still confidently produce the product and say it will work for 50 years, it's nothing like it. You have brought economy in the equipment construction. So that is what has been achieved. And let me tell you, these figures are, once again, as I mentioned, are the real figures of 500 kV coaxial cable. I brought it from Japan at something more than 30 years back, when it was being produced by one of the Japanese companies, Mitsubishi. And these are real maximum and minimum field intensities which exist in cross-linked polyethylene cables. So when we go further, Emax and Emin you have calculated. The uh, wait, what do you have to calculate next? Emax and E minimum, then calculate the Schweiger factor and the capacitance and the charging current. Let's do it. Yeah, the Schweiger factor. Eta is, as I mentioned, E mean by E max. E max you have calculated, and mean, when you do E mean by E max, this will work out to be Ri ln Ro by Ri, because the voltage, in fact, in both for E mean and E max is the same. U naught will be cancelled, so this can be worked out with this. Ultimately, the Ri ln Ro by Ri upon uh, Ro by Ri. Hmm? Let me work it out. No. Let me work it out. Is U naught divided by R U naught divided by R? Yeah, I got it. Ro minus Ri. That is D, isn't it? So this should be Ro minus Ri, not Ro by Ri. So that gave me the doubt. And 1 upon E max will work out to be U naught. This is Ri ln Ro by Ri. So this cancels. So this will be Ri ln Ro by Ri divided by Ro minus Ri, which is equal to nothing but D, the thickness of the dielectric. Make this change, and you should, I hope you have calculated taking the right equation. So that gives you the Schweiger factor. Schweiger factor works out to be 0.549, and the capacitance for this will work out to be, yeah, correctly, 2 pi epsilon naught into epsilon r, and upon ln Ro by Ri. Ln Ro by Ri works out to be 51 by, yeah, 51 by 17 is 3, isn't it? Ro by Ri. And 2 pi, 2 pi epsilon naught is 8.854 into 10 to the power of minus 12 farads per meter, mind it. And the epsilon relative permittivity of the XLPE, you can take it to be 2.3. You can consider it to be 2.3. This is also I have mentioned in the lectures earlier. And into when you have to calculate per kilometer length, you are being asked per kilometer length multiplied, because farad per meter it was, and now you need it for per kilometer multiplied by 10 to the power of 3. The farad per meter is the value of the epsilon naught. So that works out to be capacitance to be 116.5 nanofarad per kilometer. The capacitance of the cable for 1 kilometer length will be 116.5 nanofarad. And the charging current, then you have to calculate the IC is equal to omega Cu, as I mentioned. Omega is 2 pi f. 2 pi is 100, so 2 pi pi f is this 100 pi, and capacitance is 116.5 into 10 to the power of nanofarad minus 9, and capacitance minus 9 then multiplied by U naught is equal to 500 upon root 3. This is in kV, so this is volt you have converted into, and the capacitance in farad you have converted into, and when you do this, the charging current will be of the order of 10.5 amperes per kilometer length, which is fairly large magnitude of charging current. What kind of current would it be? It'll be a totally capacitive current, and the capacitive current leads by 90 degrees to the current flowing in the resistance. So it'll be a totally capacitive reactive current flowing in the form of charging current, and that too fairly high, 10.57 amperes per kilometer. Fine. So I hope you could attempt. If you have made any mistake, now you can rectify and get the values. So let's go to the third example. Over voltages. The third chapter was that of over voltages. And the third example is given from the over voltages, generation of over voltages. You know, two kinds of over voltages are there. The produced by lightning strike, that is the current injected on the line or the transmission line of the conductors, or of the conductor of the transmission line, and because of over voltages are also produced because of the switching action at the circuit breakers. So transmission lines are very vulnerable to lightning strikes because they stretch thousands and thousands of kilometers all over the country. So although protection is given with grounded wire at the top, still it happens that the lightning finds its passage to strike upon the phase wire of the transmission line. Then the lightning strike on the earth have some preferences. Yeah, that is just now I mentioned the lightning strikes always on the metal, right? That is the least resistance path towards the ground, and the transmission line conductors are most vulnerable, and sharp, tall conductors it would like to strike upon. If it doesn't get any metallic body, then it may strike even on the ground, plain surface of the ground. It also strikes on the top of the trees, top of the buildings, and even in the buildings, if the conductor is not there, it is the corners are preferred to be the most vulnerable locations for the lightning to strike upon. So you have to solve this example that the new 800 kV, 450 kilometer long transmission line from Anupara in Uttar Pradesh near Unnao has per phase line inductance of 1.1 millihenry per kilometer and capacitance of 11.68 nanofarad per kilometer. What is the ideal power transfer capability of this line in megawatt? Yeah, the ideal power transfer capability of any transmission line, you should have, or you might have learned about it in power systems, is the surge impedance loading. That means the load to the transmission line is equal to the surge impedance of the transmission line. So what do you have to do in this case? You have to find out the surge impedance of the transmission line. That is root L by C, where L and C are given per unit length, which is provided to you. In the question B, if a lightning strike on this line injects 100 kiloamperes, 100 kiloamperes is a very large current, is not that frequent magnitude of current injected by lightning anywhere, but it can inject to the order of even 200 kiloamperes. Up to 30 amperes is very common, up to 10 amperes is still more common magnitude of current injected by any lightning strike. So we have taken in this case and current injected of the order of 100 kiloampere. Obviously, impulse current. The current injected by the lightning is an impulse current. It's not power frequency current, mind it. 100 kiloamperes of impulse current. Calculate the magnitude of over voltage generated at this site. We have covered in the over voltage protection section, that is chapter number 3 in detail, and you should be able to calculate. So you stop the video here and try to attempt the question. Obviously, when you are at home doing it, you can always consult the book if you want. You can just open the chapter number 3, you will get many things, or you have to refer to your notes and calculate. So you should make a break. I will not make a break. I'll give the solution, which you should see after having attempted the question. Okay? Yeah. The surge impedance loading, as I mentioned, we call it ZC. C is taken from characteristic impedance. Surge impedance or characteristic impedance is the same thing. There are two names for the same thing of the transmission line, and that varies for practically all transmission lines between 250 and 350. Let me tell you, on an average, you could say it is about 300 ohms. And root L by C gives you in ohms, and 1.1 millihenries into 10 to the power minus 3, and 11.7 nanofarad, that is 10 to the power minus 9. It gives you the ZC, the characteristic or surge impedance of the transmission line given to you of the order of 307 ohms. Then the surge impedance loading, the ideal power transfer capability of the line is given by as equation 1.3 in the book, and that is P3 phase. The total power in the 3 phase will be given by V square by ZC, and here V square, we take V is line voltage. It should have been written capital V square, V line square divided by the ZC you have calculated. That is 800 multiplied by 800 kV line it is. So that V square 2 times 10 to the power of 3, 2 times 800 kV gives you 10 to the power 6, that is in megawatt. It will work out to be, that works out to be 800 kV line, ideal loading of this order, 2085 megawatt. So this this power 2085, people have done wonders by compensating the line capacitance with the help of reactors, etc., by series capacitor compensation techniques. So many techniques have come up. We can increase the power handling capability of the same line. We can increase from 2085 megawatt to great extent, something like, even you can say, we can increase by something like easily 25% by making the compensation for the various type of powers. But this is considered to be ideal loading. And the overvoltage produced when the lightning strikes, you must have seen by this time, when the lightning strikes on a point in the transmission line, there are the lightning current. The current will in this direction. Current will proceed in either direction. It will not go towards one. We assume that half the current goes on towards right and half the current towards left. And on both the sides, depending upon the magnitude of the current and the surge impedance of the transmission line, which is the same on all the sides, on both the sides, half the current will be able to flow. So this is given as half Li, that means the current injected by lightning multiplied by Zc. So that means this is the gives you the volts. So both the sides, half I Li into Zc magnitude of over voltage will be produced. So when you give here 100 kiloamperes, half multiplied by the surge impedance 307 ohms, it gives you in volts. So in terms of kilovolts, in terms of kilovolt, it is 15.350 kilovolts or 15.35 megavolt. Imagine the over voltage produced is in megavolts, very high. Obviously, we have considered very high current also, but it can happen. So you have to make arrangement that such high magnitude of over voltage is grounded as early as possible. If it is grounded, only the residual voltage across will be able to proceed further. But this over voltage produced, we have learned, proceeds in either direction, same magnitude. We call that to be traveling waves, in the form of traveling waves. And the traveling wave of such high voltage should be grounded as early as possible. The first place to ground is across the first insulator string. That is why we provide on all insulator string a kind of an horn gap, 2 electrodes on either side of the insulator string from high voltage towards the ground. So there is a flashover in air between the 2 electrodes, protecting the insulator string, and that grounds the over voltage. And the over voltage is grounded. So and still the residual voltage across the string will keep on travel in the direction it has started, and in the process at every insulator string, flashover will take place till the magnitude of the traveling wave over voltage subsides to the level, and then ultimately it reaches the substation where it is grounded with the help of lightning arrestor. That is the protection system we have learned across. Okay, with this chapter number 3, we make a break here, and I'll then proceed further. I think we'll have to take 2 more lectures for this to finish the number of examples I have planned to convey to you. So we will meet in the next lecture after the chapter number 3. We have to proceed till up to chapter number 10. There will be about 10 more examples. From 4 to 10, at least 10 more examples are planned out. Thank you very much. We'll meet in the 40th lecture in our series next. I can give you the example so that you can attempt. Yeah, it would be worth it. Breakdown in gases. Because you have to make a break, I'll not give you the solution. So what will be the breakdown strength of atmospheric air for small gaps 1 millimeter and 1 centimeter gap distances, very small, you can say up to maximum 1 centimeter gap distances. Breakdown strength of atmospheric air in small gaps up to say 1 centimeter, and large gaps of 20 centimeter. When we consider it to be longer gaps, it will be completely different, and under uniform field conditions and under standard atmospheric conditions. That means you do consider uniform field electrode system. You remember the uniform field electrode system, we take it. Let me draw it again. You to take the paddle plates and give the profile at the brims. What profile we had talked about? Rogowski or Boda profile, and this is the gap distance D. This is the gap distance D. So I'm asking you up to 1 cm, when the D is up to 1 centimeter, and when you increase the gap distance to 20 centimeter, and under the same uniform field electrode you are considering of atmospheric air. So what will be the breakdown strength? You have to learn and give a reply. So this is the fourth question, which the solution we will be discussing in the next lecture. Okay, thank you very much. We make a break.